Next, coming for the types of electrical loads. Okay, so in the electrical system, actually, we are having three different types of loads. One is nothing but the resistive load, one is nothing but the inductive load, and one is nothing but your capacitive load. So we have to understand what actually this resistive load is, what actually is nothing but your inductive and the capacitive load. Because as an electrical engineer, the thing is nothing but you have to find out the total connected load of the building. So by means of these three concepts only, we are going to find out the total connected load of the building only. So what is meant by resistor first of all? Which opposes the free flow of electrons in the limit resistor. So I can say that it is a physical quantity which opposes the free flow of electron, and resistor also typically used to convert the current in the form of energy such as heat. Means whatever the amount of energy from the electrical point of view we are converting to heat energy, those are nothing but your resistive equipments. Those are nothing but your resistive load equipments. Like in our homes we can see we are having water heater, we are having incandescent lamp, etc., etc. Okay, so we are having different equipments. So whatever the equipments which converts the electrical energy into heat energy are nothing but your resistors. And here the voltage and current, V stands for the voltage and I is nothing but your current are in phase for purely resistor load. Means what? By means of phasor diagram, okay, by means of simulation output, we can say that the voltage and current are in phase. Okay, for purely resistor load, it's a power factor. What is power factor? The angle between the voltage and current. What is the amount of lead angle we are getting? What is the amount of lag angle we are getting? That is nothing but power factor. Is unity means efficiency. In short, I can say power factor is nothing but efficiency. Okay, power factor. Hopefully, electrical people can understand this very easily. But for other department people, assume that power factor is nothing but efficiency of any system. Okay. So right now in the market we can see no device is purely resistive in nature, because for every device we are having inductive nowadays. So because of that we are not getting any kind of 100% pure inductive, pure resistance. Okay, and the units for the resistor is nothing but ohms. This symbol is for the ohms. And the example of resistive loads, as I have told you, that water heater, incandescent lamp, etc., etc. In the olden days, we can see we used to have a water heater, okay, which we used to immerse in a bucket to boil the water. Okay, I'm talking about that water heater, because in today's era, in today's generation, we are getting a water heater. In that water heater, we are getting some inductive value also. I'm not talking about that. In the olden days, almost like 10 years back, we used to have a water heater, which we used to immerse in a bucket or any container to boil water. I'm talking about that water heater. Again, the incandescent lamp. Okay, this is a type of lamp which we use in the olden days. For example, if I'm using this lamp, okay, even if I ignite this lamp for almost like for half an hour also, you cannot touch this lamp with respect to your hand. Okay, we require any kind of insulation like a cloth or any other insulation material to hold this. Okay, so in short, I can say that the form of energy from electrical it has been converted to heat. And the phasor diagram in the sense the simulation output. Okay, so here you can see this is nothing but the positive cycle, this is nothing but the negative cycle. Okay, this is negative cycle, this is a positive cycle. So with respect to the frequency point of view, we can say that the voltage and the current are starting at 0 degrees. Okay, the one cycle will be of how much? Nothing but positive cycle will be 180 degrees and the negative cycle will be 180 degrees. Okay, so voltage, this is nothing but the voltage, this is nothing but the current. The voltage for the complete system will be constant. Okay, you can see the V stands for the what? Nothing but the voltage. I stands for the current. So voltage and current both are starting at 0 degree and ending at the same concept. Again here the current also starting at 0 degree, ending at the same concept. So we can say that the power factor is almost like unity over here because there is no angle. Okay, so power factor, nothing but efficiency we are going to write in the terms of cos phi. So what is a phi value? Nothing but angle value. So we are getting angle of voltage and current as 0 degree. So we know that cos 0 is nothing but 1, nothing but 100%. So for purely resistive load, the cos phi is nothing but 1, nothing but 100%. So there will be no loss in the system if you're going to use these type of equipments. Whereas if you're going with inductive loads, we are having some losses. So what is meant by inductive? Nothing but which opposes a sudden change in current and stores current in the form of magnetic field. Okay, for example, I'm having a machine. Okay, so what the machine will do? It will draw excessive amount of current. Why it will draw excessive amount of current? Because it is inductive in nature. Okay, let's take an example, simple example. For example, in your room, okay, or in my classroom, I'm having some 4 lights. In the same 4 lights, I'm connecting a machine also of something like 2 HP. Okay, 2 horsepower. So whenever okay the lights are on, whenever I switch on my machine, you can see that you will be getting a flicker on the light. Okay, you can see that the brightness of the light will go, or else you'll be getting some flicker in the light. Okay, why? Because the machine has taken the maximum amount of current. Okay, because of some inductivity. So to overcome that, again we have to provide any kind of reactive power component, nothing but a capacitor for that. Okay, so in the machine we can see we are having magnetic fields, nothing but a winding concept. Because of that, it will take excessive amount of current because it has to charge. So electromagnetic fields are the key to the inductive loads. Within inductive load, the current waveform is lacking the voltage waveform. Here we can see, okay, the concept of that. So inductive load is loads which pulls a large amount of current or an inrush current. Okay, so whenever you are using any kind of inductive loads, so the major drawback is a limit, it will take maximum amount of current. So, and the units for the inductive is a limit Henry. And here you can see, as I've told you, the voltage will always start at 0 degree only. So what the current is happening? It is starting at 90 degree because from this point of view till here, it is taking maximum amount of current. Okay, it is taking maximum amount of current. This thing can vary, but as an example, I'm taking this value. Okay, that depends upon the load and the manufacturer. So what is the phi value we are getting? Nothing but 90 degree we are getting. So cos 90 is how much? 0. So for purely inductive load, if you are using a pure inductive load, in that case the efficiency will be 0. And the example of inductive load, nothing but your fans, your pumps, motors, welding machine, etc., etc. Because in all of these equipments we are having inductive. Okay, because in all these equipments we are having inductiveness for that reason. Okay, wherever we have a winding, in short we can say that is nothing but an inductive load. Along with that inductive load, we have to connect which load? Nothing but capacitive load to overcome the inductiveness, to improve the power factor value. So what is capacitive load? It opposes sudden change in voltage and stores energy in the form of current. So if you want, so whatever the amount of extra current is required, okay, so that we are providing the means of a capacitor, so that the other loads will not get disturbed. The capacitor is nothing but the capacitor bank or synchronous condenser. We are having two types of capacitor, nothing but capacitor bank or synchronous condenser. Capacitor bank we are using inside the building for our personal use. Again, the synchronous condenser we are using for the transmission point of view. Okay, to maintain the power factor value. So which are used for the reactive power compensation. Reactive power in the sense nothing but the enhancement of the power factor value to improve the to remove the inductive value. So the capacitor has a current waveform which is leading the voltage waveform. Okay, here this is inverse totally. Therefore, the voltage peak and the current peak are not in phase. To enhance the power factor, we use capacitor bank. You can see a weight. Okay, so here you can see the voltage starting with the 0 degree. Okay, but previously, as of capacitor, whatever the excess amount of current is there, it will take from the capacitor. This is the area of the capacitor. Okay, so from here it is taking, again coming with respect to this, again it is going from here to here. That means we can say that whatever the extra amount of current is required to your inductive load is provided by means of a capacitor. So I can say that the phi value is in minus 90 because we are going to the second quadrant. So for that reason it is minus 90. The cos minus 90 is setting again 0. Okay, so again this value will vary. Okay, it can be 60 also, it can be 70 also. That depends upon the load and the manufacturer. For assumption purpose, I have to take 90 degree. So example of capacitor, nothing but the capacitor bank and the synchronous condensers. These are the different types of loads what we are having in the electrical systems, and different examples what we are going to see. Okay, along with this we are going to see many more loads also in the future classes, inshallah. Next we can see the different voltage level present across the globe. Okay, see, in different countries, in different areas, we are having different amount of voltages. Like for example, if you're talking about low voltage, so whenever we are talking about low voltage, means the voltage which lie between 220 volts, 230 volts, 415 or 440 comes with respect to low voltage area. If you're talking about the normal voltage, means what? 3.3 kV, 3300 volts. Okay, 6.6 kV, 6600 volts, or 11 kV or 13.2 kV comes with respect to normal voltage. When you're talking about high voltage, means the voltage from 18.2 kV to 33 kV is called as high voltage range. For extra high voltage, 66 kV and 132 kV. Yeah, Mr. Anup. Any doubts for you, Mr. Anup? Okay, so extra high voltage in the sense 66 kV to 132 kV. Again, for modern extra high voltage, nothing but 220, 400, 440. Again, for ultra extra high voltage, nothing but we are going with 765 kV. So these are the voltage ranges. Okay, almost in every country we will have this value only. So as a beginner, if you are new to this field, then you have to remember these values. Okay, this will be the interview question also. What is the range for the high voltage? So you have to say that 18.2 kV, 22 kV, 33 kV, etc., etc. And for example, if you're working with a country like India, okay, and as we know, we are having single phase and three phase supply. So whenever you're working with single phase, that means we are having a voltage of 220 or 230. Again, for the three phase, we are having 415 or 440. Okay, for the three phase. Again, the frequency. What is meant by frequency? Number of cycles per second is called as frequency. Means in 1 second, how many amount of cycles we are getting with respect to positive side, with respect to negative side. Okay, just now we discussed the phasor diagram now. With respect to that, I am talking about. For UAE, okay, nothing but 220, 230 for the single phase. For three phase, 418, 440, 380. Again, the frequency will be same. For Saudi Arabia, it's 220, 230, 418, 440. Again, for New Zealand, okay, especially for the European countries or for the Western countries, the voltage range will change. For the single phase, it is something like 120. For three phase, it is something like 220. Okay, again, the frequency is 60. For Australia and all, it is 120, 220, again the 60 hertz. The frequency is 60 hertz. Okay, so this is a voltage range which I have given for some countries. If you want to go with respect to some other countries, you can check online. Okay, etc. And in 90% cases, the 11 kV is generally used as point of supply. For example, I am working with respect to a building. Okay, I assume that this is a residential building. So I'm having a transformer. So for transformer, we are having two sides. One is a high tension side, one is a low tension side. Okay, so at the high tension side, generally we provide 11 kV point of supply. From the 11 kV point of supply, we will step down the value to something like 450 or 440 as per our requirements, as per our regulations. Okay, because we are using transformer only to step down the voltage and to maintain the frequency, for that reason only. So the input side we are using 11 kV. At the output side we can go with 415 or 440, etc. etc. That depends upon the country, okay, as well as the regulation.